In the previous session, we have seen that open structure of glucose. Now, in this session, we will see that there are some of the reactions in which the open chain structure of glucose is not giving these reactions. Means the glucose have the cyclic chain structures which are giving all these reactions. Now, as in open chain structures, aldehyde is present, so glucose will react with sodium bisulfite and ammonia. They are the weak reagent, but this reagent is not reacted with these structures. Even it does not react, it does not give the Skiff's test, for which is the special test for aldehydes. Means it will react with the aldehyde to give bright red product. But the Skiff's test and 2,4-DNPA test both are not reacting with the glucose. This means the structure is not a open chain structure. It is not even reacting with the Grignard reagent. It is not forming glucose pentastate with ammonium hydroxylamine. Previously, we have seen this forming glucose pentastate acetate in open chain structure, but this the structure is not shown by with hydroxylamines. Even the structures react to give two isomeric glucosides, which is obtained by heating glucose plus methanol in presence of dry HCl. So, in presence of dry HCl, we are getting isomeric glucosides in alpha and beta. For what is alpha and beta, we will see just now, because this only confirms that aldehyde group is not present in the molecule. Some other group is present. So, what is that groups or structures? So, a scientist called as Emil Fischer, after so many properties, he confirmed that the glucose is the open structure glucose. This is CHO. So, this lone pair of on oxygens, so it is reacting with the carbon like this one. You can see here this is the carbon, and the lone pair reacting to the center of the carbons here, and hydrogen from the fifth carbon will goes to the oxygen of the first carbon. So you can see this carbon is sp2 hybridations, but when this bond is broken, this carbon is converted into sp3. So these two carbons are sp3, and it forms a cyclic structures. So under 30 degrees centigrade, this D-glucose structures, will convert into this type of cyclic structures after combining this oxygen with this intramolecularly with this carbon 1. You can see the hydrogen is shifted to here. So there is two possibility of hydrogen shifting over this side, and one is this side. You can see both structures are same, but the position of hydrogen after combining with this oxygen carbon 1, so there will be two positions. One is inside the ring, one is outside the ring. If it is inside the ring, it is called as alpha D glucose. D means dextrose glucose, and one is your beta D glucose, because this is outside the ring, and for these structures the open rings must be heated with hot and saturated aqueous solution, that is temperature is almost 100 degrees centigrade. So one is 30 degrees centigrade, you will get the alpha D glucose, and one is almost 95 degrees centigrade. More than 95 degrees centigrade, you will get your beta D glucose. Beta means the OH is outside the ring, and alpha means OH is inside the ring. This is the open chain structure. So these two rings are equilibrium to each other. So when you heat at 30 degrees centigrade, you will get the alpha, and when you again increase to more than 95 degrees centigrade, you will turn into beta. So these two are in equilibrium condition. You can see the alpha D is first converted open chain, then it is beta D glucose. So these are the 6-member ring, and each having the 5 chiral carbons. So previously was 4 chiral carbon, now they have 5 carbon. Even this carbon was also, this carbon one was also counted as the 5th carbon. So specific rotation of this alpha D glucose was 110 degrees centigrade, is 110 degrees. So what will happen? So this will decrease to become 52.5 degrees, that is become open chain structures. And beta D also, it is also increased, it is 19.7. Specific rotation is also increased to 52.5 degree. So their side beta D to open chain structure is your increasing specific rotation, while alpha D it will decrease to 52.5 for equilibrium conditions. And one more thing, alpha D glucose is 36%, is very less, but beta is 64%. This is more. Why? We'll see later the reasons why the beta D glucose is more stable than that of alpha D glucose. So alpha D glucose and beta D glucose are the anomers, okay, so that differs in OH group at the hemiacetal carbon. So what is hemiacetal carbon? Hemiacetal carbon is this carbon is called hemiacetal because it is attached with the OH and OR. Here this is OH and OR, so this carbon one is called as hemiacetal carbon. So sp3 carbon is hemiacetal. So how we can get hemiacetal? So hemiacetal means when you take any alcohol with the aldehyde, so the alcohol part react with the aldehyde, addition will take place, nucleophilic addition take place, it will form acetal compound. Hemiacetal means this carbon contain OH and OR. You can see from this color. Similarly, if you take the two molecules of alcohol reacting with the aldehyde, so you will get the OR. So again this hydrogen replaced to give water. So cyclic structure in internal addition of alcohol in aldehyde group. So you know hemiacetal and acetal, these are the two products when aldehyde react with the alcohol. Alpha and beta forms are epimers of each other at C1 or any other carbon that we have already seen, but anomer is what is a special type of amer that differ in configuration and specifically at the hemiacetal and acetal carbon. Just we have seen in previous lecture what is hemiacetal and acetal carbon. So alpha D glucose-pyranose and beta D glucose-pyranose, so these are the hemiacetal carbon. So what is the pyranose? This we will see after this studying this following session, in this session. So generally hemiacetal, these carbons are unstable. So but in 5 and 6 member, when this acetylene in form of 5 and 6 member ring, they become extremely stable. So these two are a stable cyclic glucose. So epimers and anomers both are diastereomers, you have to remember. Hence ring structure, it will explain all reactions of glucose which was against open structures. Okay, so and all these structures were studied by the Emil Fischer. After studying, he gave the reactions. So this is the hemiacetal, you can see here. This is the cyclic structure of alpha D glucose, and after addition of methyl alcohol in dry HCl, so this H part you can see here, OH plus H, it will give you water and you get this structure. So this OCH3 and O, this is your hemiacetal. So this carbon is our hemiacetal carbon. So this is called as alpha D methyl glucoside. And if you take the beta glucose, so beta glucose means OH is again opposite side outside the rings. This is beta glucose, again presence of methanol and dry HCl gas, you will get the OCH3 outside. So this is called as beta D methyl glucoside. So with reaction of methanol, it will give alpha and beta dimethyl glucoside. So it also explains the muta rotation. Muta rotation means alpha D glucose after sometimes it becomes equilibrium mixtures, and after standing this equilibrium mixture, it will automatically in hot and saturated solution, it will becomes your beta D glucose. So after sometimes alpha D convert to equilibrium mixture, if you give heat it becomes a beta D glucose. So percentage of beta D glucose is more than that of alpha. And specific rotation already we have discussed. So when slow change in the value of specific rotation, this one, that is alpha D glucose to equilibrium mixture, and equilibrium mixture to beta glucose, or beta D glucose to equilibrium mixture, and equilibrium mixture to alpha D glucose. So in this state, what specific rotation also changing. So plus 110, it will decrease to 52.5, and it will increase. It will again decrease to 19.7. So again it will increase. Again it will in this case will increase to 110. So this is a changing of optical rotations is called as muta rotation. So this phenomenon only happen in your carbohydrates. And beta glucose, why it is stable? So it is stable. So we will see later on that due to the position of the OH at equilibrium position. We will see in next session. Now we will see the method to determine the size of the glucose rings. So Fischer and Tollens, they proposed the ring or internal hemiacetal that is formed between the carbon 1 and carbon 4. That is called as furan type or Furanose structure, which is nothing but the 5-member ring. Here I have drawn the diagram for this Furan structure. You can see this is a Furan structure and it is a 5-member ring. Next scientist Haworth and Hurst. These two scientists were there. So he also described the ring between the C1 and C5 type of is there. C1 and C5. That is called Parana type, or it is called as a Pyranose 6-member ring. This is the Parana structures. So you can see here how this lone pair attacking on the carbon to become your this Pyranose structure, 6-member ring structure, and this carbon is sp3 is called as hemiacetal. So now you will easily understand this diagram. What is pyranose and your hemiesters. You can see it when OH is this side, this is called as alpha D-glucose, and when OH is outside the ring, so this is called as your beta D-glucose. First carbon is your anomer carbon. So we can write, so when OH is inside the ring, so this OH, this whole OH part of right hand side is down the ring. So first you draw this ring, put oxygen this side, and again to arrange, and this is your fifth carbon attached with the CH2OH in upward direction. Now all OH should be down and one OH should be down. So we start from here. So this is the down, then again second part is again down, this is OH is up, again this is down, and then again CH2OH. Similarly, in this structure, this is the glucose alpha D-glucose-pyranose 6-member ring. In this case, the first carbon OH is up, so up is your beta carbon, so beta your glucose, and then the second is your down, remaining same as the alpha carbon, alpha D-glucose. So beta glucose, alpha D, only position of anomers are there, means this position is only changing. So group on right hand side take downwards. So those group which is right hand side always consider as a downward direction. So please keep this, remember, like this is up and down. This side is up, this is down. Pyranose representation also called as the Haworth projection. So this is the like a Haworth projection. This is a pyranose. So if we always keep this oxygen upside, not downside. So on keeping, this is the beta glucose, and we can also represent in terms of your you can say chair form conformations. This chair form conformation, again oxygen you can see up is there, this is down, this is down. So this is 1 2 3 4, and all are in equatorial position. You can see here everything's in equatorial position. So that's why this beta glucose is more stable than that of alpha D glucose. So this is anomers. So this keep up, again this is the structures, and OH is down position. This is your up is your beta, and this is your alpha. So this position is called as alpha, and this is your beta. So alpha, you can again alpha anomer, you can write this like this in the chair form, but here OH is in only this OH is in axial position, the remaining all are in equatorial position. That's why this is your less stable, and this is more stable because all OH are in, all groups are in axial, sorry, equatorial position. That's why this is beta anomer of glucose is more stable than that of alpha anomer. So in beta D-glucose, all OH substituents are in equatorial position. Axial position is occupied by all hydrogen, which require little space and little steric strain. So this is more stable. While in alpha D-glucose, one OH is bonded to anomeric carbon in axial position, and alpha glucose is less stable than that of beta glucose. Already we discussed all these things, so this is just for your revision. In free state, all monosaccharides are exist in pyranose forms, while in combined state, some monosaccharides such as ribose, 2-deoxyribose, and fructose, etc. usually exist in furanose form. Triose and tetraose have open chain structures. We will see some diagrams of the glucose. Here in this diagram, you can clearly see this is the your D-glucose, and oxygens convert. So it is going to this carbon, hydrogen shifting to here. So we will get two structures. One is pyranose form, and second is furanose form. This is the 5-member ring, and this is your pyranose, your 6-member ring. So glucose is turned into two type of forms: pyranose forms, and second is your furanose forms. So two type of structures possible for the glucose. The pyranose form of the glucose dominates, that is more than 10% at equilibrium in aqueous solutions. You can see here this pyranose forms. This alpha and beta both forms are there, and 10%, and open chain structure is very less amount, and furanose forms are very, very less percentage because this is not that much stable. Both are glucose structures there. So this is more stable. These two are very less stable in aqueous solutions. So this is the another form writing same things. Furanose structures. This is the acyclic forms, and this is the pyranose form in your chair form model. This is very clear, and this is the alpha and beta position. So if alpha is up and beta is down, OH group will be down. So this OH decides with the alpha and beta form. So here is one more different example. D-glucose have two structures, furanose and pyranose. So you can see pyranose is alpha and beta, and furanose is again alpha and beta. So but the amount of furanose for glucose is very less, and this is only more stable. But we'll get the both the structures. So this is the board conformation of the glucose. You can see here all this we have seen in isomers. This is the flipping of the chair and two chair forms. So again you can see here, this is the most axial of glucose. This is again both form of glucose. Oxygen is top position, here oxygen is down by flipping this one, and this is your chair form and board form. So same structure in the form of chair and same in the form of board. You can see clearly, understand what is the equatorial position. This is all are equatorial positions. That's why this form is more stable than that of your beta alpha forms. Alpha form in which OH in axial position. So chair form, this is called beta D glucose, is more stable. Tests of glucose, when you heat when you are heating a dry test tube, so it will melt and turns browns and finally black, giving the characteristic smell of burnt sugar. This is the one of the test. Second, when you are warming with a little concentrated H2SO4, so it is leaves a charred residue of carbon. This is the second identification of glucose. When you are boiling with dilute sodium hydroxide solution, so it is first turned into yellow and then it becomes your brown black. Second is our Mollis test. So already this test for carbohydrates, when you drop a 2 alcoholic solutions of alpha naphthol and again in 2 ml of glucose solution, and then thereafter 1 ml of concentrated H2SO4 is added carefully along the sides of the test tube. Then there is a formation of the violet ring at the junction of these two liquids, and this violet ring, so will confirms the presence of carbohydrate. Second is our silver mirror test. So in this silver mirrors, a mixture of glucose and ammoniacal silver nitrate is warmed in a test tube. So appearance of silver mirror on the inner walls, it only confirms the glucose. And the next is failing solution test. So a little glucose is again warmed with the failing solution. So you will get the red PPT of the cuprous oxide. So that red PPT is your confirming the presence of glucose, because this is the test for aldehyde. OSA Jones is also one of the important test for glucose. So glucose, when you heat with the excess of phenylhydrazine in acetic acid, it will give you yellow crystalline compounds, and its melting point is 478 Kelvin. So these are the different tests for the identification of glucose. Now we will see the use of glucose. It is used for preservation of fruits and preparation of jams and jellies. Second, preparation of confectionaries and sweetening agent. So it is a food for patients, invalids and children. In the form of calcium glucosate as medicine in treatment of calcium deficiency. You can use as a reducing agent in silvering of mirror, that is tolerance reagent. As a raw material for alcoholic preparations, industrial preparations of vitamin C. In the processing of tobacco, as an intravenous injection of the patch to the patients will lower the glucose content in blood. So these are the major use of the glucose.